Hey everyone, so this lecture is going to be on Thomson 4.9, which is the last section in chapter 4. It's going to cover this idea called the intrinsic parity of the Dirac fermion. Okay, and what we're going to do is we're going to learn about this thing called the parity operator, which basically changes spatial coordinates from x to negative x. But before we start talking about that, let's review a little bit about the other transformation operator called the charge conjugation, which I think we covered in a couple of sections ago when we talked about antiparticles, right? There's also a symmetry that's respected by quantum electrodynamics, which is what we're going to cover, what we're trying to drive towards, which is all the interaction of electricity and magnetism, and also respected by the strong force, which is what we're going to cover after electricity, quantum electrodynamics. And the strong force is described by this other fancy name called the quantum chromodynamics. Okay, but before we talk about that, let's talk about charge conjugation. So charge conjugation is usually symbolized by the symbol, C hat, just to be less creative as possible in naming our operators. Okay, so if you were to act with this operator at some state psi, it doesn't need to be eigenstate or anything. It basically turns that state into whatever the antiparticle state is. Okay, actually, since this is an operation, this is actually equal. Oops. Okay, right. So let's say if psi is the particle of a fermion of a Dirac particle, right? This will be described by some maybe U1. So this is even the spin up. Okay, sorry, the first component, right, e to the I p dot x minus e times t, like that, right, and it turns it into the antiparticle of that. In this case, right, this will be v1, right, if that's turning this directly, e to the minus I p dot x. That minus side comes from us flipping time, of course, for antiparticles. So we get positive energy solutions. Okay. So this is charge conjugation operation. Okay. But now we're going to explore this thing called parity transformation. Okay. Parity transformation is that, well, whenever you see x, we turn it into negative x. Okay. So whenever you see y, you turn it into negative y. And the same thing with z, where you turn that to negative z. Okay. But we don't change time. Okay, you don't touch time. Time just stays the same. Okay, this operator, right, or symmetry, is also conserved by all of electromagnetic interactions in the strong force, but is violated by the weak force. And then we'll deal with the weak force later. This for now. Let's just stick with electricity and magnetism described by quantum electrodynamic, and then in a couple of chapters we'll actually describe the strong force, which is the quantum chromodynamics. Okay, so how do we deal with this parity operator? Okay, suppose we have some state psi that's the solution to the Dirac equation. That means they are a Dirac particle. Oops, I can't even write Dirac. Right, Dirac particle or antiparticle. Let's just call it a Dirac state, right? Okay. So if we apply the parity transform to the state, what's going to happen is that you apply parity to psi, right? It's going to turn it into psi prime, where psi prime is the parity version of it. Okay, so where all the spatial coordinates got flipped. So if we were to write psi like this, right, with x, y, z, and t, right, psi prime, right, it's going to be whatever psi is minus x minus y minus z, but then t stays the same. Okay, whatever that function happens to be. Okay, so there's one more interesting thing about the parity operation, right? If I was to flip, let's just do a one-dimensional example. Let's say I have some x coordinate here, right? So x1, right? The parity operation on that flips it to negative, right? So this is negative x1, right? It flips it over here. So whatever the state we were describing here, when we do parity of it, it flips to negative on that side. But then if we apply the parity operation again, right, it will flip back to just the regular x1. So by definition, if you apply the parity operation twice, you basically does not do anything, and usually that's identified as the identity matrix, but let's not talk about the matrix yet. We will see this in matrix form, but don't think about these as matrices. Just think about them as operations that, oh, this applying the parity operation twice does not change anything about the state. Okay, so that's what this is about. Okay, so the book derives the parity operator, and it took about a page of algebra, and I really encourage you to read through that, not too carefully, but at least get kind of each of the steps and how Thomson actually derives the parity operator as actually gamma 0, as we will see. And the strategy is usually by, if I have the original state, and that's a solution to the Dirac equation, if I was to flip all the coordinates from x to negative x, y to negative y, z to negative z, how is that state described? And then we're going to work through this parity operation, changing all the coordinates, and see what comes out. Okay, and then we can actually see, that what did this actually, how did this actually affect the solutions to the Dirac equation, namely all these, the U1, V1, U2, V2 spinors times e to the I, p dot x minus et, right? So he went through a page in order to do that, but I'm going to skip that just for the sake of time. But, right, this happens to be the gamma 0 matrix, okay? Remember, the gamma 0 matrix is actually, by definition, the beta matrix we used before, and this is this matrix where you have the identity on the diagonal and the negative identity on the bottom half of the diagonal. And remember that these are 2 by 2 matrix. In other words, this is a 2 by 2 matrix. So the whole thing is actually a 4 by 4, right? Okay. And it's actually written out down here. Okay. So, so let's just see how this parity operator operates. Okay. So let's say I have some particle called, in a state of U1. Okay. Where I'm acting on this with the parity operator, okay, and the parity operator, which Thomson proved to be actually just gamma 0, okay. So this is a matrix that's going to be multiplying by this U1, okay, and remember U1 in general, okay, it's going to be square root of E plus M, okay. I'm going to have a 1 up here, 0 here. And this is where I want to make sure I look at which one has the PZ. So the third component has the PZ, and the fourth component has the PYs. Okay, PZ, E over M, E plus M, and then PX plus I, PY over E plus M. So that's U1, right? In the case where the particle is at rest, meaning P is equal to 0, this term goes away, this term goes away, okay? In this special case where the particle is at rest, right? Also, when the particle is at rest, the energy of the particle is also equal to the mass, so you actually get twice the mass here, square rooted, okay? We can write the U1 spinor as square root of 2m, 1, 0, 0, right? Because those are all zeros down there, okay? If we multiply that by this, gamma 0 matrix, right? This one multiplies by this, right? Let's just write it out on the other side here, right? Well, there's a factor of square root 2m in front as usual, okay? 1 times 1 gives you 1, okay? But the problem is that, so 1 times 0, right, gives you 0. Negative 1 times 0 still gives you 0. Negative 1 times 0 also gives you 0. Okay, I know I'm kind of skipping a lot of, you're supposed to just multiply this, multiply this, multiply this, multiply this, right? There's actually 4 multiplication you're supposed to do, but they're all zeros. Okay, so therefore, right, this is this is actually the original state U1. So what happened is that, right, the parity operator acting on U1 gives you U1 back, so it doesn't affect it, which is kind of neat. Okay. For antiparticles, okay, so p hat, let's do this for V1 just for the sake of it. Okay, once again, the particles at rest, and in fact I'm going to go back to make sure that I'm going to write the antiparticle U1, V1 correctly. So you have the PXPY with a negative sign, and then negative PZ, and then on the bottom you have 0. So hopefully I remember how to write that. Okay, since the particle is at rest, the energy plus m just gives you 2m. Okay, so px minus I py over, well, it doesn't matter because the momentum is 0. Okay, so I didn't even need to write that. Okay, and then it's the third component or the fourth component that has the 1. Okay, it's the fourth component. Okay, so we have 1 down here. Okay, and once again, P, right, just turns into this gamma knot matrix. Okay, so that's still 1, 1, negative 1, negative 1, bunch of zeros everywhere. Okay, so the resultant of this, right, is going to be 1 times 0, 0 times 0, 0 times 0, 0 times 0. So the first component is actually 0. Similarly, second, similarly, third. The only one that's not 0 is that you have 0 times 0, 0 times 0, 0 times 0, and then negative 1 times 1. You get a negative 1 here. And I keep forgetting this factor of square root of 2m in front. Okay. Okay. So this is not V1, but actually negative V1. Okay. So the parity operator acting on V1 gives you negative of V1 back. Okay. All right. All right. And similarly, if you did this with V2, it also gives you the negative back, and then U2 will also give you the positive U2 state back. Okay. So for a particle with some momentum, so let's just do that in general, right? So U1, I had it written up here. Right, let's just copy that down for practice, right? So E is no longer equal to m because we have momentum now. Okay, so there's going to be PZ E plus m. Okay, Px minus IPy. Okay, E plus m. Right, this is the 4-component thing. Okay, if we act on this with the parity operator, right, where the energy and momentum is some value, not 0. Okay, we're going to hopefully see what we expect to happen. Okay, we'll see. Okay, all right. So this giant matrix, right, 1, 1, negative 1, negative 1. And this time I'm going to write out the zeros because I'm going to have to figure out which thing I'm multiplying. Okay, and 1, 0, PZ E plus m, Px minus P plus Py E plus m, parentheses all around this, guys. Okay, what does that equal to? Okay, so, well, the first component is 1 times 1. Oops. Of course, there's a square root of E plus m, which you usually would write in front, but I forgot to write it there, and I don't want to redraw these matrices again. Okay, so square root of E plus m. Okay, big giant thing. Okay, 1 times 1 equals 1, and then the rest is 0, so it doesn't contribute. Okay, 0 times 1 is 0, 1 times 0 is still 0, and the rest is also 0. Okay, 0 times 1 is 0, 0 times 0 is 0. Right, this one gives you a negative, right? Negative 1 times PZ gives you negative PZ, right? Similarly, right, negative 1 times PXPY gives you negative PXI PY E plus M. Okay, right? So this is not U1, but it is very similar, but the only thing that changes the direction of PZ, PY, and PX, right? So this is actually equal, right? U1, oops, the parity operator on U1 energy when parity. Okay, there's the reason why I'm writing these. It's the same thing as U1 with the same energy but opposite momentum. Okay, right? You know, because this negative sign came from this. Okay, and hopefully this makes sense, right? So if I have a particle going, well, from my perspective, left to right, hopefully it looks the same on the screen, left to right, okay, going this way, right? If I flip all the spatial coordinate, now it's actually a particle going right to left now, right? So that's why this momentum direction change, and in the homework you'll get to prove this with the other spinners. Okay, so I'm gonna stop recording.